All right, so tonight what we're going to cover is the first half of our classification notes. So I've tried to condense these and make them a little bit simpler from previous semesters and kind of clarify the important parts and take out some of the stuff we didn't need. So that being said, what we're going to cover is classification. So I'm going to keep hitting the wrong button on the Adobe window. Try again. Click over here. All right. So what is classification? Basically, oh, what have you missed from the small talk? Literally nothing. Where is everyone? That's what you missed. All right, so classification. We're going to talk about text or document classification because it's one of the most important areas of text analytics. It's probably like the main goal of text analysis. Instead of building text products, like chatbot is a text product, right? But we're going to work on text analysis. And it is used to either classify or cluster, categorize, or otherwise create groups based on the attributes that are embedded in that document. It's especially useful if you have a lot of documents and you don't have time or energy to read them all. So much like a search algorithm is meant to give you the best results first, this allows us to at least group results to know what's going on. But the work is, useful for documents, but this, classification overall is a very popular area in data analytics and machine learning, so it can be applied to music, images, videos, all kinds of stuff. But we're going to focus on features and embeddings when it comes to text. So we have called things all semester like tagging. Right? That's part of speech. We did, sometimes it's called chunking or entity recognition or NER. We just finished parsing, so we did sentence parsing and then dependency parsing. And all of those things are basically specialized forms of classification. Right? So they're classification with a known set. So it's nouns, right? Verbs, adjectives. Or it's a set of entities that you're interested in finding, or it's noun phrases and verb phrases. So most of text analytics, when it comes to the analysis part, is a special form of classification in some kind of question. And so the stuff that people really like is sentiment analysis. That's next week. That's just a specialized classification question as well. So we're going to avoid sentiment today, but we'll cover it in a couple weeks. The one thing we haven't really covered, though, is feature extraction. So today we're going to talk about how to build a classifier and talk specifically about text feature extraction, because mostly we've been focusing on feature extraction at the word level for our parts of speech, at the kind of chunk level for our named entity recognition, where you had to label the beginning and the end of the sections, and then at the whole sentence level for our parsers. Excuse me. And so the feature extraction has really been those different pieces, but now we have kind of the sky's the limit. But we'll focus on the most popular ones. So our main goal here is to take some sort of data, documents. And when you use the word document very globally, it could mean tweet, it could mean scientific article, it could mean Library of Congress. So document just means any kind of text piece that represents a unit of text for your analysis. Okay. If you combine all those together, you get a corpus. Okay. So documents can be sentences, or they can be entire novels if you wanted. So we're mostly going to work at the level of small documents, but like I said, the sky's the limit. You just have to have a computer that can process all this stuff. Now, before, the classification labels had to be a specific thing, right? Nouns, noun phrases, verb phrase, person, GPE. Now they can be whatever we want. So we could perform classification on pre-labeled data. This is supervised learning. That's mostly what we'll do this week. Or we can work from unlabeled data, which is unsupervised learning. We'll do a little bit of that next week. Okay. So there's two different types of classification. However, all the stuff from the earlier in the semester still stands. all of your documents will need to be cleaned or normalized before trying this classification stuff. It just gives you better results. Okay, so some terminology before we jump in here. What can I classify? Well, we could classify individual words. That's what part of speech tagging is, right? But if we've kind of ignored the traditional NLP stuff, generally individual word classification comes in for sentiment, right? So this word is the word that should go in our positive category, and this word is the word that should go in our good category. So if you're familiar with the LIWC, the Linguistic Inquiry Word Count software developed by Pennebaker and colleagues, that kind of is how that approach works, right? It counts the number of words that go into each of these categories, right? So happy, sad. I think it's positive and negative emotion actually, but then they have some like cognition and time. So they have these specialized categories that we're trying to classify words into. Okay, they've done that, and then they're now using it in a slightly different way. We could want to classify phrases or sentences. And this is how a lot of programs like Grammarly sort of work, right? So under the hood, they're looking for these phrases that you're using that are overused or colloquial or not formal enough, and then trying to help fix your grammar. For the LIWC, what's the name of the author for the LIWC? It's Pennebaker. And it's spelled L-I-W-C. No problem. We could classify tweets, and that was very popular for a while. I mean, still popular, but like there was like this weird time period where I felt like everybody was doing sentiment Twitter. And there was like this cool website that I don't totally remember where that would like tell you how happy and sad different celebrities' tweets were, right? So Twitter's still a popular way to data mine because it's open by its nature, right? And it has less ethical issues than using Facebook, for example. And so a lot of people will mine Twitter to look for different effects, different things. And then we could go into what most people consider a whole document. So one project we've been working on that one day I will finish is we've been trying to find ways to help us search for data sets that should go into our corpora list. And what we've done is taken all the abstracts, scientific abstracts, from our original data set, matched them to abstracts that didn't go into our data set, and then built basically a classifier. Should this go into our data set or not? And so that's bigger than a phrase in a sentence. We could classify the whole article, but we've gotten pretty good scores by just classifying from the abstracts. So I often have some sort of predefined class that I'm interested in classifying documents as. So let's say you're working with software like Jira, right? Or, GitHub issues, whatever, and you want to label each issue that is reported to you. Well, you probably have a set of predefined classes that you're interested in classifying those issues as, right? Bug fix, technical support, billing, that kind of stuff. So we could use those predefined classes. If we're doing sentiment, we might be interested in positive, negative, and neutral. We could be interested in the type of article it is, sports, fiction, news, academic. We'll do a kind of an example of that today. But really, it's whatever keyword that you like and you have a data set for. So the problem with data sets continues. Then, on the other hand, what you might do is use something like a topics analysis, which we'll cover just very briefly touch on next in the sentiment section. Or topics or cluster is also popular, not so much with text data, but is a popular unsupervised task where you're actually using those documents to sort of reveal what the classifications might be. And so topics is really useful for this, where it sort of helps you figure out how these documents are related. So these are the ones that go together. Now you figure out what the label should be. That's an unsupervised approach. And you could start with an unsupervised approach and then move into supervised approaches. So let's see. Oops, I thought I had a label up here. An example, a very, very classic problem, right, is the spam filter. So, every good mail system has this sort of spam filter technology where they're trying to figure out from, their underlying huge database of emails and what you mark as junk to build a classifier that helps sort out your inbox and your spam folder. As an academic, I find this kind of funny because there are tons of emails that I get that they look kind of like journal emails. So I'd like to keep the journal emails because they tell me important information, like my article has been accepted or it's been published, or I got to go back to the drawing board, right? And then there's tons of these like for-profit kind of scam journals that send me stuff all the time. Okay, they buy my email from some list somewhere, and I get tons of this stuff. And so it has a very hard time, at least Outlook, since our emails through Outlook, has a really difficult time distinguishing those two types of emails from each other. Okay. The, foreign person dead in another country that wants to give me millions of dollars, that one's gotten to be easy. But there are some subtle distinctions that are still quite hard for spam emails. Right? So what might we do to help us sort this out? Okay. Well, I could use an unsupervised task to help maybe see, is there something about these for-profit journal emails that is subtle but different enough that I could use as my filter. So I could take all of these emails, put them through an unsupervised task, because I don't have them pre-labeled maybe. Okay. And the focus there would be on pattern finding. What is the latent structure in the data? So latent here meaning underlying distribution, basically. So this underlying structure where all of the for-profit ones, right, tend to have a very long list of journals in them. Okay. So they're like, hey, come publish in our journal, and we also publish all these other unrelated things that you don't do, right? The journal emails that come directly from an actual well-established journal, from Sage, for example, don't tell me all the other things that they publish. So that might be a pattern that I could find. The other one is maybe the publishing country. And there is a pattern there as well. So we could use that pattern finding, okay, and use feature engineering to find these meaningful patterns. Okay. A lot of this work can be qualitative in nature, meaning sort of thematic analysis. This isn't really covered a whole lot in analytics because people don't like to do stuff by hand so much. But, topics analysis is meant to mimic this sort of qualitative work that is more computational in nature. And some other options might include clustering, topic models. We've already talked about factor analysis for continuous data. So just finding a way to have it group things together and see if you can see the pattern that's there. Sometimes that pattern is purely mathematic, and you may not get how it's classifying them. That's happened plenty of times to me where I've had a topic model that just didn't make a whole lot of sense. That happens. Some other techniques might include our supervised tasks, and that's what we're going to focus on here. The problem with supervised tasks is you do have to have a gold standard, right? You have to have a pre-labeled data set with those categories already defined. That either means creating your own, which we've seen over the last couple of assignments is tedious, or at least in sentiment analysis, there's a ton of these. So the internet has done well on creating nice sentiment training data sets. And your business or institution might have some of this. Here's some data that we have already worked through by hand. Build us something, a program now that will do this. Our features are going to be extracted to help us predict those categories. And technically, at its base, this is regression. Okay? We're going to do some fancy regression. So we might do logistic regression. Okay? And then all these other like machine learning algorithms are just different forms of math. And so I've kind of been interested lately in the obsession with ML and making it sound like this magic. And I'm like, it's just math. It's just fancy math, lots of predictors. Because maybe we're not interested in how the job is getting done, but as long as it's getting done. So to me, the kind of big divide sometimes between sort of traditional, the way I was taught science and academics and sort of data analytics is I want to know why it works, right? So why did this analysis work? Why is the prediction working? What does that then tell me that I can do more research on? But for business solutions, you may not care at all why it works as long as it continues to work. And that's really where machine learning is quite helpful because it will often work. Okay. Will it generalize to new samples? Maybe. We'll see. It's a good test. But you can often find the right combination of tensors or predictors that will give you a good answer. But then to me, the real interesting part is why does it work? Hey, maybe it doesn't work like we want it to. So there's all this really great research right now on algorithm bias. So understanding, where did our data come from? What are the biases that are already in the data? And then what are the biases that we're creating by creating this algorithm? If you're interested in that kind of stuff, Kathy O'Neill has a really great book on this called Weapons of Math Destruction and tweets a lot about this stuff. So, at its base, regression, technically a form of supervised learning. Right? So, that's where we're just trying to predict some continuous outcomes. So let's say you're trying to predict, you can't predict stocks. That's stochastic. That's a different type of regression. But let's just say we're trying to predict, corona cases. Also a bit stochastic. But, that's a continuous outcome we're trying to predict. But that's supervised learning, right? You have the answer and you're trying to figure out what it is. Classification's the same problem, but instead we're just trying to predict some sort of a label instead of a continuous outcome. So, how are we going to make this work? First thing we're going to do is define our feature extraction by determining what might predict the categories. We're going to specifically here focus on bag of words methods, and we'll look at word2vec. And then I'll say that you could do nearly anything. Okay, you could very simply count the number of words in each document. Okay? You could count the number of characters in each document. You could look at average word length. You could look at average sentence length. You could look at the number of ends that are in the document. If you think those things might be useful. Okay? Probably not, but I do think there's some interesting things to be said about length, document length, depending on what you're trying to do. Okay? So Twitter is a great example here, right? Where there's probably some level of something that will help predict. Let's say you're trying to predict hate speech on Twitter. This is a big problem that they're always trying to solve. And what would I expect? Well, I might expect that the extremes of the distribution are helpful. So we're either calling people dirty words, right? Or we're writing these rants. So length might be useful. However, we're going to go a little bit deeper than that. Okay? We're going to use some distributional semantics to think about feature extraction. Once we pick the feature extraction, we move on to the algorithm. Okay, to see how we can map the features to the labels. This is picking the math. Log, Bayes, and support vector machines are the ones we're going to look at. Sorry, I was trying to figure out what that noise was. And then once you pick an algorithm, you'll use that labeled data, and we'll split it up into a training data set that'll allow your model to do the learning part. basically calculate the weights for each of those predictor columns onto the outcome. And then what's happening is we're tweaking the parameters. Every model is slightly different here because, each type of math has a slightly different way that it predicts, right? So Bayes and log are pretty different. But at their base, what you're doing when you are learning is tuning the parameters in the model. Okay? Now, that's a one-shot process in something like log regression because it's a closed-form solution. It just calculates. Okay? If you're working with something like a deep learning model, you actually tune each time. So when we talked about spacey and training a spacey model, we said with each training run, right, I think it does back propagation. Don't quote me on this. Where it guesses the answer and then goes back and says, well, I got it right, so strengthen those parameters. Or, oh, I got it wrong, tone those parameters down. So it tweaks with each run. And we calculated our losses to see how well we were learning. Right. Most of the models we're going to do here are sort of like calculate and go, but you could do deep learning models on these types of data as well. Okay. So I don't want to step on our machine learning class's toes though, so we're going to just kind of wade into the water. How do I do this with text? And if you're really into this, those classes will teach you a lot more on the different types of algorithms and considerations. So we've trained it. Is it any good? Okay. So we could look at accuracy. We'll also talk about precision, accuracy, recall, and then the F1 score is what it's called. Okay. And this is similar to, your statistical testing. We would say, well, we've built this model for regression, for example, and is the overall model any good? Is it predictive? So we might use p-values, might use r-squared. We'll see. And that's akin to what this is. But the other thing we'll do, this is the same thing, is take that testing set and see if we can improve our model. And there's lots of things we can add on here. Cross-validation, leave one out kinds of models, lots of small samples. So sky's kind of the limit here. But that's the basic procedure, right? Extract your features, pick an algorithm, train, test, evaluate. Okay. Now, in this particular two sets of bullets here, I'm talking about a development testing set and a final testing set. Okay, this is where you take your training, your big data set, you train, and you have a smaller data set that you see if it generalizes. And if it doesn't, you tweak. You try to figure out what you could do differently, update your model, change things, okay? And kind of go back and forth between test and dev test, train and dev test. But we should always save a final data set that we only test on. Okay? This allows us to not cheat one, but also overfit our models. Now, what can we learn? Well, we can predict two classes. Okay, this is a binary choice. This is the simplest type of model we could do. Like in my example, does it go into the data set or not? We could do multi-class classification. Okay. So logistic regression at its core is so good at binary prediction. Okay. We could also do a multinomial logistic regression where we have 3 or more categories, but you're still assigning each document to one category. Or there's actually multi-label classification as well. We won't get into multi-label. I would say if you're interested in multi-label, you can actually take this multi-class classification schemes that we're going to talk about, and instead of only looking at their final choice, most of them will give you a probability a probability number. So let's say we had 3 choices, positive, negative, neutral. Right? From most of these algorithms that we're going to look at today, I could tell it just give me the most probable answer, and it'll pick one. Well, we still have those probabilities underneath. And in multi-label classification, there's lots of ways to do this, but one thing you could do is simply look at the probabilities and say, okay, anything over a 30% probability in this example, we'll give it both labels, that kind of thing. And that kind of analysis is really good for keywords, where we might assume that each document has multiple topics in it, and we're going to give it multiple keywords. So the process. I love this picture. I don't know why it's so large. I don't remember where I stole this from, but it's so great. We're going to zoom out so we can see it all at once. This is like, to me, one of the best pictures that really encapsulates everything that we are trying to do. So for supervised learning, we have some sort of training classes. The example we're going to do today is the 20 news groups data set. It's essentially like trying to predict Reddit categories, okay, from old news groups. And we've got some that overlap in the sense. So we've got like 3 or 4 that are about, PC tech kind of stuff, 3 or 4 about sports, and 3 or 4 about religion. So can we distinguish between these sort of subtle categories? So the training classes involve the simply which news group it was in, right? So if you want the modern day equivalent, which Reddit subreddit is this on? We've got the training documents, the actual text that people wrote. And the very first step, normalize. I love that they have this first. Text normalization. This really depends on the task. But in our example, we'll do sort of our traditional set of steps. Okay, not spelling because this is internet chat, but everything else. We're going to spend a good time today talking, and next week talking about feature extraction here. What are the most popular feature extraction methods? What is the easiest? Once we extract those features, we now have a set of training features. This is a data set with many columns. And we give it to our algorithm, log, right, Bayes. So it's got the classes, it's got the features. It's going to build ourselves a model. From that model, we run through the same steps this way. So we've got our documents that we do all the extraction on. We say, hey, here's some new stuff. You predict. It gives us some set of predictions. And we say, okay, well, here's the answer. How well did we do? This picture is perfect. It shows you the whole process all together. So I'm going to print it again later and come back to it as a reminder of what exactly we're trying to do. But most of the focus today is here going to be on feature extraction. Okay, and a little bit on the algorithms. All right, well, let's try it. Whoop, I'll make this a little bigger. All right. So I've just loaded up everything I need from Python. You should see most of this should be familiar, right? We've got pandas, so I can load the data sets. We've got beautiful soup to take out the HTML. We're going to stem, or we could stem with our Porter stemmer. We could take out stop words. Definitely want to take out stop words. Unicode data. Okay, so we can decode any weird symbols and contractions. So none of this should be a surprise. And so the 20 news groups data is essentially like an early Usenet website. And it's a data set that has different news groups, different Reddit threads, right? Hockey, hardware, politics. Okay. And then also has the article that we're trying to predict. All right, so the question here is, do we have the same machine learning algorithms for this, like support vector machines? K-nearest neighbors is an unsupervised one, so no on that one. Or do we have separate ones? No, they're pretty much the same. We're going to do logistic, multinomial Bayes, and support vector machines today. So the math part isn't really different. It's the getting to the math part. And when I look at the 20 news groups data, it's a difficult task because 20 categories is a lot of different categories to try to predict. Right? I'm happy sticking with like 2, yes or no, but you might be trying to distinguish between these categories. But we can already tell they kind of overlap. We have some good tech ones, There's politics, there's sports, and there is a good number of religion ones as well. So we're really testing here to see if we can create an algorithm that can distinguish between these very similar categories well. Okay. It might be very good at getting the like big gist, but can we narrow better? So I'm hoping that you can see here that there's a bunch of formatting that we don't want. Okay. So we've got these /ins for the enter key for new lines. We've got some numbers, and then if you look at the whole thing, there's like lots of formatting that we don't want. Okay. The other thing here is that once you clear out a lot of these text issues, it might be that you end up with an empty post. So one thing, or an empty document. So one thing you will really need to do is at the end of any text normalization is remove empty posts. Okay? Or the code that you run after that will be very unhappy. So there needs to be some characters there and not blank ones. Okay, and I'll show you that specific line here in a second. So I ran this chunk. It's quite slow. Well, it's not that slow, but it can be slow. So I ran this separately and saved it. But, here we go. We can take out all of the HTML code that might be in there. And one key here is to notice this string function. Okay, so over the semesters when I've taught this, we've run into this issue where sometimes it just doesn't interpret the text in one of these panda cells, right, or text in general, as a string. It interprets it as a byte-like object, is the error message you usually get, or the string is all numbers, and so it interprets it as an integer, which is no fun. So in all of these cases, we're going to just tell it to convert to a string every single time. It seems a little repetitive, but you will get way less errors this way. So we're going to beautiful soup and get text for every row in our data frame. Okay. So this looks a little different than what we've done before because we were, working with one document before. And now we have a bunch of documents, so we have to loop over them. So we'll take our pandas series or pandas column and convert it to a list. This just runs so much faster. There's some things you can do with series and some things you don't. I'm not quite the best at it, but when you convert to a list, it works great. So, get the beautiful soup for each one. This does throw a little bit of an error in the newest version of Beautiful Soup because it's a little angry at me, but it runs fine. So I looked at the warning and then moved on. So you might get a warning running this, but it should be okay. All right, now I'm going to lowercase that. Well, it has a function. Dot string to make sure it's a string to lower, and I can apply that function to this series. Okay. There's two different forms of contractions that we can do, and I can't remember which one I taught you, so I've included both. Right, I think we did this first one. So contractions.fixed for each text. Right. You can also do this kind of combined loop where you say, okay, for every possible contraction, replace it. And they actually run equally fast. It's a little surprising because this loops over each possible contraction, and this one loops over each possible row. And I have found that they tend to roughly be the same timing. Okay. It's not this step that's slow. It's the stemming step that's slow. Then we'll do our crazy Unicode, right? Normalize into ASCII, decode into UTF-8. We'll take out any special characters. This is a little bit new here, but we're going to take out anything that is not a alphanumeric or a digit. Okay. And so here, this just is like some fancy code to say anything that is a weird character we don't want. We're leaving in punctuation, but we're taking out some other random characters. In this one, I am going to stem. Okay, so use our Porter stemmer, stem for each word in our text. We're splitting on white space. for all of our text. Sorry, I keep hitting the wrong button. So we're going to take all of those and remove all of the stems, all the S's, all the INGs, all the first stems like UN, what else? ED, that kind of stuff, the Y's. Then we're going to take out the stop words. We probably could combine these two together, but it's maybe a little bit easier to keep them separate so you know this is stemming, this is stop wording. And then the key component here that you don't want to miss is this thing. Okay, there's two ways to do this. First object, and this is essentially R's version of subset and sort of drop. Okay, so the tilde is say everything, drop these rows. Okay? So if the article column in our string dot strip, okay, strip removes all the extra white space stuff, is empty. Okay, basically if it's an empty string, drop that row. And that will, you put that at the end so that, you know, if by the time we got done through all this decoding and taking out stop words, we're left with nothing, we aren't trying to extract features from a blank text, because that won't work. Now, the other thing that you can do is do drop NAs, because sometimes they end up with blank cells, and sometimes a cell ends up as an NA, a missing data. So we need to drop both. And then I actually wrote this out. You don't have to save this. I only did this because, like, you know, when you're running Markdown and you have big files, right? I don't want to run this over and over and over again. So I ran it once. I turned this chunk off and wrote it out. Okay, so when I look at it here, wait, it's like, whoa, why do I see ngram? We're not there yet. See here I have eval equals false. So I'm still showing you this code, but I ran it manually once and then said don't run this again because it takes like 5 or 10 minutes. It's not the end of the world kind of slow, depending on how my computer's feeling that day, but you guys don't want to sit here in class and watch that. So if you're cutting and pasting code from here, make sure you're either following the same steps where you run it and output it, or you take out that eval equals false. Okay, so what did that do? Well, now we can see that we end up with this sort of uninterpretable kind of weird text, but all of those codes are gone. The stemming does make this more difficult to read, right? So pretty here, the Y becomes an I. This is confusing, right? And so it basically has converted this all into now at least somewhat similar. And having a stemmer or a limitizer is a really good idea here because it combines like forms. But if you're going to look at it afterwards, it does make it hard to know what any of this is saying, because we've removed all of the support words, all the stop words, and then we've converted all of the semantic words into a sort of halfway root form. But we're not ever going to use these again. It will use them underneath in the math, but we won't look at them again. So, Now, I question sometimes whether or not the stemming is worth it. So we've tried several models where the stemming just doesn't add anything. But that might be because we're using scientific text, and the words aren't repeating at a frequency that it matters to combine like forms. If you're using text from people talking, I imagine it might matter. But that's the nice thing about these systems, is you can turn it off, test it, turn it back on, test it, and see which one works better. All right, so let's get started. We're going to take this into scikit-learn, and we're going to import the train test split function. Okay. So the train test split function just allows us to split our data set into testing and training data sets. We could then split our training data set again, right, into dev test and test, but we're going to stick with just test and train here. And the way you do this is kind of nice. So on the left-hand side of the equation, this is one thing Python really has kind of wins for, is you can put as many variables as you're expecting to get back. Okay? So I'm going to do train corpus and test corpus. Okay, that's the actual text part. Train names and test names, that's the label, y, what I'm trying to predict. And so it's going to expect 4 chunks of information back. So what we do is train test split. Now you do have to convert this from pandas to a NumPy array. Okay, so this is numpy.array here. And we say, my mouse is being, or my touch screen is being so sensitive tonight. Okay, so we're converting to a NumPy array. The first one is for our article. Now this function here, apply, this just applies a function to the data set, and this mp.string converts it into the right string format along the way. It's essentially doing like data-df article dot string, but this is a special NumPy string. It's not always necessary, but every once in a while NumPy will just get mad at you from experience, and that will just help make sure we're still in strings. Even if we're left with numbers, keep this stupid thing as a string. So we're using strings the entire time. 1 second, I'll answer that question. That's a good question. Okay. The other half that kind of ran over to the next line is the second piece. Okay. So you're putting in train, test, right? And the trust function, train, test, split, will take the first one and split it into 2. And then it'll take the second one and split it into 2. So it knows that these are the first argument and these are the second argument. And the second one is the target name. Since we know there aren't any numbers in our target name, we didn't do the special lambda string thing, but if you're having trouble, you can try adding it there too. The key here is that sometimes your text is numbers, and it will convert those into something else, and it'll throw an error, but way later. And so this is one place that I know we've had problems, so I just want to really highlight this section. Now, test size here, I did as 20 for our 80-20 split. Random state, this is every programmer's textbook's favorite joke to make this a Hitchhiker's Guide. Number of 42, it is a random number, you can pick your favorite number there. And then I just printed out how many we have in each one. Train corpus shape, test corpus shape. This tells us we have, it's a single column here, 15,000 in one and 3,000 in the other. So your question here, how many do we need? It's a great question. I don't have an answer. I feel like I'm reminded, I took a class on item response theory once, and I asked this exact question. How many people do we need? He said, well, if it runs, that's how many you need. More is always better. More examples produce better models, because more examples will have more instances of those idiosyncratic moments and make them more generalizable. Okay, so they'll work better on new data sets. That being said, sometimes you just don't have that much data. So, if your model works, it works. So I don't have a good answer for you. So the model example that I've been talking about that we're doing on academic papers, I think our test, I think we have like 2,000 text examples. And so our training data set was like 1,600 or something like that. And it worked pretty well. Okay. If you're trying to classify from 12 examples, maybe it won't work so well. But it's a testable hypothesis. So the bigger the better, and there's no real good number here for what the minimum is. I'm sorry, my answer is I don't know. The answer is it depends. Does it run? Then that's enough. But more is always better. All right, well, given the limitations of your computer, right? So in this example, this is a manageable size that we can run. And if you have like 8 bazillion tweets, like it'll say you had 8 million tweets or something, that's going to take a long time to run. And so it might be better to sample from that. Okay, so if I can not click on the wrong spot, we need to make sure that we don't have any empty or very small categories. So this is actually a great, your question is a great segue to this slide where I will tell you that it's probably more important to not have empty or very imbalanced categories. So in any case, I don't know if you guys are familiar with chi-square, which is the sort of statistical test for categorical data. Right. One of the biggest concerns in that kind of analysis, and conversely with log regression, is having a category that's very small, okay, and predicting it against a category that's very large. Because let's say we had, to use COVID cases, for example, 100 negative tests and 5 positive tests. You will get it right 100 times out of 105 if you guess all of them as negative. And we'll get to how those numbers are calculated, where we can kind of think about prediction accuracy. But if you have a very small category, you need to make sure that that category has enough examples for your model to work. Because it will always be harder to predict the smaller category because mathematically it's advantageous to just always guess the larger category because you're still getting it right. And so we'll look here when we get to classifying these at each category separately, because you can have an overall model that predicts better than chance or predicts at maybe some level that you might consider good, but never gets one of the categories right. And so I used to have this example of spam, trying to predict spam text messages. And people would tell me the model was really good because it would get 80% right. But they were ignoring the fact that it never got any of the spam ones right. That's not a very good model. So models need to be able to predict each category at least well enough. And so I would argue that maybe the size of the overall data set is not the most important component, but the size of the individual categories. So if you have a data set with a large imbalance and you can't do anything about that, what I would do is pick a system that would allow you to train in batches and give it more balance, right? So do some crossfold where you select a smaller number of the larger category. So you randomly pick 100 from the large category and, the 20 from the smaller category so that you're not creating this heavy difference between the two. All right. An empty category is really bad because then you don't have any examples of it. Yeah, there are a bunch of ways to handle this situation where we're trying to balance data. I mean, not bootstrap. Bootstrapping is probably one of the easiest ones. With text, you got to be careful with bootstrapping because then you're showing it the exact same text twice, which does happen. So it would depend on what kind of text that you have. So like, if I had a bunch of tweets, I would say bootstrapping would work pretty well. Okay, if you aren't familiar, bootstrapping is this idea where we take randomly sample from our data set with replacement, okay, under the assumption that each row is something that is representative of a larger set of data out there in the world. But if I'm doing scientific articles, that may not make a lot of sense because it's the exact same one, so it just kind of would depend on how much you believe each text piece was repeatable. And we've already kind of talked the way at the beginning of the semester about how creative humans are with language. So I don't know if they repeat in the same patterns. Now, there is a lot of repetition in patterns in text, though. So I could argue both ways. All right. So back to this, though. So counter is a package that we can use to count. Okay, it makes tables for us. It's real nice. So what we do is make a dictionary of our train label names, and this counter function just literally makes us a key value pairs of the text and how many there were. So this is really pretty much like using the table function in R. Do the same thing for our test label names, and then all this magic pandas code here lines them up. Okay. So for each key in our dictionary, we're going to print the key, so each target label, the number in our training set, the number in our testing set, and loop over them. And then here I've just got to give the columns some names and sort them out. So let's make sure this isn't going crazy. So this is pretty good. Okay, in our testing set, we have a fairly equal distribution of our different options. Our training count, we have a lot more religion than we do religion, actually interesting, but that balance is not too high. Okay, what's too high? Depends on the task. I hate saying it depends all the time. It's very statistician of me, but in a traditional log regression, I say 10 to 1 starts to be really problematic. With text, it tends to work a little better, but once you start getting in those higher ratios, it's bad. My answer is always try to run it and see what happens, and then if it never gets any of these categories right with the low counts, that's when you need to start trying some either bootstrapping or random sampling or something different. So always try it first and see. And then the answer might not be the feature extraction is the problem. It might be the way you're training the model. But this is not bad at all, really. I mean, this is the lowest one, but they're all fairly even. Cool. So we don't have a problem there. And this is enough text to try. So let's try it. And we've been talking about feature extraction. We haven't really gotten into what that is. So what are features? Well, I've talked about how it could be the number of characters, it could be the number of vowels, it could be the number of nouns, right? There are lots of things here we could consider, but a feature itself is something I can put a number to. So I have a friend that does qualitative data analysis, like a real qualitative data analysis. She's always making fun of me when I say, I do qualitative stuff. She goes, yeah, you spend all your time converting them to numbers. I'm like, well, that's how this works. So converting text to numbers. Generally, this is something that is counted or coded as binary, and so it's present or not. Okay, sometimes this is called one-hot encoding when it's coded in this binary fashion of either available or not. We could talk about dummy coding in regression, contrast coding. There's lots of cool ways that we could do this. Okay. And really what we're trying to do is figuring out how to transform this text data into features. And that is so heavily dependent on the task. I'm going to show you here some components that you can use on any text, but I would encourage you to be creative in these questions, because for your business example, you might simply be like, if it has these 3 words, it's a billing question. Okay? And you don't have to go fancy. So it's a simple regular expression, one-hot encoding question, right? So these don't have to be crazy, but we're going to do the kinds of systems that should work on most text types. All right. That being said, what we're doing is bag of words methods. I love bag of words. It's one of my favorite things. I would be very hard to convince me that this isn't some sort of voodoo magic. What is a bag of words? Well, what you do is you take each document, each text piece, and you create a column for it. Right? Then you create a vocabulary. Here are all the possible words across all the documents. Now that we've done all this normalization, words, documents. Then you fill in the numbers in the middle. Okay. Bag of words is so beautifully simple. It is a crosstabs is SPSS. Conditional frequency distribution of words as either rows or columns. It doesn't matter which way the matrix is, but where you have the vocabulary and you have the documents, and the numbers inside that are either a one-hot, meaning that word is present or it's not, or they're a frequency count. How many times does that word occur in that document? Sometimes this is called just a count method. Okay, so when we look at this function in scikit-learn, it's going to be a count vectorizer. But this kind of approach is called bag of words. Why is it called bag of words? Well, the idea here is that you lose all context. So the biggest criticism of bag of words methods, which is totally valid, is that context, sarcasm, any kind of word meaning embedded is totally lost. Because we take all those words and we shake them up and you just have a count of how many times each word occurred in each document. With the underlying assumption that you know a word by the company it keeps, this is a very famous phrase, and words that are present in documents together are probably matching. So if document 1 has the same words as document 2, they're probably about the same thing, is the basic idea. Now that's problematic the longer the document is, personally. Like tweets, oh yeah, these two tweets have the same words, they're talking about the same thing. Once you get into like whole novels, you're talking about changes in theme, changes in topic. Right? And that's where a solution becomes doing each chapter, if you're working with big text pieces, or each paragraph becomes a document so you can break them up. But let's say you're trying to classify the entire document, right? So there are different approaches there, but the basic idea being if the same words are present, it's probably about the same thing, so we should give them the same label. So things with this label have these patterns, things with that label have these other patterns. But the criticism being context is lost. We will also talk about a model that will allow us to keep context, though, as a contrast to bag of words methods. But bag of words methods are very popular because they work. So we could try a bag of n-grams method. And that's where we take bag of words, but instead of using single words, we might use phrases, okay, or n-grams. So 1 gram is the bag of words method. So 2 grams is 2 words at a time, 3 grams, 3 words at a time, etc. But it's the same approach. Documents, phrases, count how many times each phrase occurs. Oh boy, the problem with this though is that it does expand the feature set, which might be useful. Okay, so you get more rows. But the internal frequencies of that matrix become very small. When you do a bag of words method over just a normal one, a 1 gram, you have what's called a sparse matrix, meaning there are a lot of zeros. Because, this word may only occur in these 2 documents, and that word may only occur in these 4 documents. Because we've eliminated all the words that occur in nearly every document, like stop words. This is really why you got to eliminate stop words there. Definitely not helpful in these types of models. They add a lot of noise if you don't take them out. So sparse matrix. Okay. That's okay, but the more you become phrases, the sparser it gets. And so you end up with matrices that you may not be able to see the patterns for the trees, basically, because the frequencies are so low. And the solution to that, the sparse matrix problem overall, is term frequency inverse document frequency, or tfidf formulas. I would say that you will see, if you're ever searching for this kind of stuff on the internet, you will see tfidf everywhere. It's very popular, but what is it? Right? It's actually a transform. So the approach is still bag of words, but we know that the sparsity of the matrix may cause us issues. So it's a normalization procedure, transform procedure. I don't know the best way to describe this. That essentially converts our frequencies to numbers that represent the importance of a word into a document. Okay. So you can look at the formulas for these, and I would say that there is some argument over the way that scikit-learn has implemented their formula versus more traditional tfidfs. But either way, Effectively, what it does is it looks how frequent the word is across, totally, right? And how many words are in each document, and creates this sort of importance metric. So if a word is very, very frequent, it tends to dampen down that importance. Because if it's in a ton of documents, it's not salient, it's not unique enough to be a good predictor. Um, or if a document has only 4 or 5 words, each word might become very salient. So it kind of looks at the matrix across and down. And so basically it's a weighting scheme, that's a better word for it, that is applied on top of bag of words. So you calculate a bag of words and then you tfidf. That's traditionally done on a frequency count, not a one-hot matrix. But you could do it on both. Tell me, okay, we're good. So some other ways that we could extract and vectorize the data include word2vec. Word2vec is a very popular simple neural net model, and we'll actually do one of these. It was developed by Google, and it encodes the data to capture context in a simple neural net. A simple neural net has one input layer and one output layer. We'll cover this a little bit more next class. Deep learning models have multiple hidden layers. Okay. Simple models don't, they have one. And word2vec is very popular. Okay, so we're converting words into vectors. Okay. Those vectors represent the weights for those words, predicting their context. But we can take that information and use those vectors as our predictors. So these were originally developed to help predict word context. What word should come next given this context? But we've taken them and like converted them into these feature extractors. And the most important thing about word2vec over bag of words is this context issue. So it allows us to grab context in 2 different forms using either a continuous bag of words approach, called SIBO, or skipgram. I will explain those more when we do one of these models. Some other forms, GLOVE, I think is Stanford's. Fast text is Facebook's version of word2vec. Are tweaks on word2vec options. And the nice thing about Gensum, which is the Python package we're going to use, is that doing a word2vec and doing a fast text are very easy comparably. Like fast text has a command line version and I think their own Python package. I find them both a bit obtuse. Gensum is so magically easy. So you could decide, I want to try both, and create vectors for both. Okay. So we'll use Gensum for a lot of our distributional semantics models. That's what these are often called in the sort of nerd area, right? Because we're creating a distribution of the words by documents. All right. So what are some popular classification algorithms? So we've covered the text normalization already, and then we've covered the feature extraction now. What math might we use? Okay. In our example, we will do multinomial naive Bayes, and I'll talk about each one that we're going to do as we run one of these. Okay. And logistic regression is probably the most popular way, right? Support vector machines, kind of, to me, a newer to me, right? But then there's random forest models, gradient boosting machine models, and more. So I included 2 links here. They might be a little out of date now, but either way, they just talk about some of the more popular algorithms that are out there. So there are a ton of them. I will say, in summary, of these different extractions and these different models, is sometimes what I find is the added complexity of a more mathematically intense model does not save me anything. Okay, so a lot of interest in deep learning right now. Those models take a long time to run, to crunch, in my own experience, to do stuff, and that complexity often does not give me a much better classification, for example, that a bag of words methods didn't do. So it always tell you to start with a simple approach because simple approaches run faster and that makes businesses a lot happier, right? When you're using less computing power and less time, um, and see if you're getting added um, classification bonus by creating these more complex models. So let's keep it simple, right? Keep it simple. Okay, so let's do like 2 more slides and then we'll call it good for tonight. So evaluation, how do I know if this model is any good? Well, we might check the accuracy of a model. One second. So we might check the accuracy of our model. So accuracy is a measure of simply percent correct, right? So we have the answer in a supervised learning task, and we have the guess from our model. We just calculate percent correct. So accuracy is really easy. That only works if we're doing a supervised task. From that, we can also calculate precision and recall. So these are two sides of getting things correct. So when I get things correct, how much am I getting it correct versus missing it? Okay. So we're going to look at like the proportion of them that we got correct divided by the portion of them we got correct and the ones plus the ones we missed. Okay. So maybe we're getting, when we guess the category, we're getting all of our guesses are correct, but we've missed this huge group of them. That's no good. And then the other one is essentially when we guess and we get it correct versus when we guess and we've guessed it wrong. Okay, which has come a false alarm is sometimes what that's called. And we'll use some examples there of like how those are calculated. Okay. And then an F1 score, which is the harmonic mean of precision and recall, because precision and recall have different denominators, so I can't just like add them together and divide by 2. And so it balances the one you have more information from. All right. So all of that we're going to put together in a confusion matrix. And so confusion matrix is really a great way to see what has happened. Because what it does is it calculates the times that you got it right for that category versus everybody else. So in our example, we have 20 categories. A confusion matrix, we can create a big one, but essentially we would say, okay, how many times did we get category number 1 right? How many times did we miss category number 1? How many times did we guess category number 1 and it was a false alarm? We shouldn't have. And how many times did we get it right by guessing everything else? Okay. So this just really allows me to see how many times I've missed something versus how many times I sort of overguessed. And so it denotes that predicted label versus the actual label, one versus compared to everybody else. And this is where one would investigate a model that is poor. Where am I getting it wrong? Is it in a logical way? Or is it completely illogical and I need to rethink my feature extraction? If it's logical, then maybe some tweaks to the feature extraction. So, you know, this category was religion atheism and we guessed it religion misc. That's a near miss. Okay, it's close. But this one was religion and we guessed IBM peace, support. That's not quite right, so maybe I need to throw the whole thing away and start over. All right, so we're going to start here next time so that it goes with the math calculation. So what we'll do is have the actual math for what is accuracy, what is recall, precision. And so we'll start here with this really lovely chart about confusion matrix and talk about true positives, false positives, and kind of relate this back to statistics since you've all had a stats course. And we can also talk about how this works in like hospital kind of settings. So when they're developing vaccines, for example, what kinds of things, what are those numbers that you're hearing on TV and how do they work within this framework? So this is where we'll start next time. We're about halfway. And then we'll also do all the code for calculating these different statistics. Okay, questions. I will also apologize. It's like a zoo in here, everybody. Um, can you hear the dog barking, cat running around? Okay, one sounds good. Anybody else? These are the same thing as type 1 and type 2. Exactly. Indeed. So there's a couple different ways that people describe these. So in stats, we talk about type 1, type 2, and power. So we'll cover that next time. But in like hospital settings, we might talk about like sensitivity and specificity. Sometimes people use positive predictive value and positive negative predictive value. So there are kind of different areas, call them different things. But yes, it is similar to type 1 and type 2. Nope, no added flavor. I think it's interesting how, um, in stats we spend a lot of time focusing on type 1 and power, especially, but in machine learning, we're really interested only we don't really talk about the negatives very often. Right? You're really interested in the positives part. So each group focuses on different pieces. For me, it's more interesting to think about what a test that is sensitive and specific, right? So, like for example, an HIV test, right? You want that to be sensitive so that when you take it, you get a positive. You know that's right, and you also want it to be specific, so it doesn't it accurately distinguishes with the positives and negatives in a way that is. Oh, see, now I've gotten specificity. Hold on, now we gotta look it up. Right? All right, so sensitivity is a cross, I think, right? So true positive rate, right? Where it tells you, like, if you get it positive, it is what it is. Specificity is the other way, true negative rate. So if you don't have the condition, you're correctly identified as not having it. In machine learning, we don't care so much about the true negative rate. Other stuff. All right.